A very pleasant good morning to all and welcome to 5 days faculty development program on innovative research and development trends in electronics and communication engineering organized by Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management, Greater Noida. This event is technically co-sponsored by IEEE UP Section India, IIC, Start in UP, and AKTU. I, Dr. Asta Sharma, on behalf of EC Department, welcomes Galaxy of Intellectuals, Your Excellency, Chief Guest of the Day, HOD Sir, Director Sir, HODs of other departments, faculty members, and dear participants. Thank you for taking time out and being here today. We are very grateful to have Dr. Shashi Poddar as the chief guest of the day. The agenda for today's talk is sensor fusion and its application for navigation of autonomous vehicles. Before starting that, I would like to give a brief introduction of our department at GL Bajaj to let our speaker and participants know better about us. So kindly let me just share my screen. Is my screen visible?
Yes, ma'am.
Okay, thank you. So before starting about the EC department, a brief introduction of GL Bajaj Institute of Technology and Management. We are one of the prestigious institutions under the GL Bajaj group of institutions. It is one of Uttar Pradesh best engineering and management colleges, and it is known for providing its student quality education and great placement opportunities. The institute is approved by AICT, MHRD Government of India, and is affiliated to AKTU University. The Department of EC Department visions to become a department of repute and prepare globally competent and socially responsible professionals with holistic knowledge and technical skills under the mentorship of Dr. Satyendra Sharma, HOD of Department of EC. Our department is NBA accredited, and we offer BTech course of undergraduate course, and this department has been established since 2005. The department has always exerted the best of its efforts to meet the objective of achieving technical excellence in areas of electronics and communication engineering. These are some of the highlights of our department. Since its inception of the institute, our department has also been established at 2005 with 60 seats, and now we are seeing ever increasing number of seats from 60 to 180. And also we are delivering the best results. Number one in Uttar Pradesh. We are proud that recently in 2021, our ranking has been the top in delivering the best result. This is the research highlights of ECE. We have here 5 research groups, 20 plus patents had been filed or published. Our students are being so dexterous. They have granted or awarded around 15 lakhs in student projects. We have here 11 laboratories, 6 advanced laboratories, and our department faculties and students are always being hardworking and delivering. We have around 300 plus research articles, and our faculties are very sincere and they are delivering the best of the research. So these are the highlights. We are also focusing on 360-degree on student development, encompassing of various elements of the spectrum, that is state-of-art laboratories, highly qualified faculty. We are also organizing annually international conference MedCom, and this year the conference is going to be held in October, and we are receiving huge participation and registration of papers, not only nationally but also internationally. We are also organizing international webinars, trainings, FDPs, and various certain such kind of events to develop the personality of faculties as well as students. Our students also go on industrial visits, internships, workshops, and trainings. We are offering 100% placements and alumni interactions. We offer industry-centric internships with good hands-on skilling. We also focus on the development of the student personality, and so we have here in the department extracurricular activities done by Anvita Club as well as TechBlitz Club. We invite renowned people from IITs, NITs, in academics field or in industry experts to offer to deliver innovative and to sorry to make us understand the current industry trends and value added courses, and we are also offering school outreach program. We also at the department have NPTEL local chapter, ICEIT, GL Bajaj student chapter, IEEE chapter, department newsletter, and journal. These are the best brains to mentor the bright minds. We are very proud to have such dexterous faculties. So these are the list of the faculty. We also have 6 laboratories here, which is industry focused to make our students industry ready. Cisco Networking Academy, Technology Incubation and Development Center, Center of Excellences in Biomedical Image and Signal Processing, as well as SDR and MIMO systems, Research and Development Lab, CNC-based PCB routing. And these are some of the glimpses of a student's achievement. We are very proud that one of our student, Kajal Srivastav, her project was selected amongst only 5 projects from Pan India to showcase in front of Prime Minister Shri Narendra Modi and Prime Minister of Israel, Mr. Benjamin Netanyahu. Our students are also participating on various platforms and are winning accolades like in Anveshna Delhi NCR 2021, as well as Startup Awards, Atal Incubation Center, and NXG Ventures. They receive fund of rupees 10 lakhs through Atal Incubation Center and NXG Venture. They are also participating in divisional innovation exhibition where they bagged prize, which was supported by Council of Science and Technology UP. Our students are also participating in hackathons. This is the picture which is showing that they have won first prize. Also, our students are not only participating in the competition, but they are also representing as delegates in various global platforms like in Women Economic Forum. Then our department has signed MOU with ALTTC BSNL Ghaziabad. This is the highlight about the placement at of the department. We this year had record breaking placement of 92%, highest package 18.2 lakhs being awarded by the Cisco, and these are some of the top recruiters for EC 2021 batch from Cisco, Bosch, Ericsson, Hawaii, Tata Technology, Essential, Cognizant. So these are various top recruiters for the current batch. Our students are also very creative, and they are venturing out into the entrepreneurship journey, and they're establishing their own startups. So this is the student for us. You can see. And we are also very much working on organizing such events to develop the faculties as well as student personality. And these are some of the successful events which we have organized, and we got huge participation from not only nationally but internationally from 24 countries. And we have also got appreciation from major countries like Italy, Malaysia, and USA, UK for organizing such events. We also offer industry visits to students to go and learn from leading industries like ST Microelectronics, ALTTC Ghaziabad Electronica, Uniconverge Technologies, Ministry of Electronics and Information Technology. These are some of our notable alumni where our students are placed in reputed places and are serving at reputed organizations like Indian Army, Air Force, Airport Authority of India, ISRO. They are in Malaysia, Canada, they are all around spread globally, and we are proud to have them as GLB family. So this is all about our department. If you want to reach us, you can contact at this given email address. This is all about our department. I will not waste much of your time. And now, one minute. So I would request Dr. Kirti ma'am to please introduce a speaker for today to the participants.
Sure, ma'am. Good morning, one and all. Am I audible, ma'am? Am I
Yes, ma'am.
audible to all
Yes,
of you?
ma'am. Yes, ma'am.
Good morning, one and all. Myself, Dr. Kirti, and I'm very glad on introducing the eminent speaker of today's morning session, Dr. Shashi Poddar. He is my first research guide and mentor during the MTech, who always guided throughout my research with his knowledge. He has received his BTech in Electronics and Communication Engineering from SRM University, India. He completed his master's and PhD in Instrumentation Engineering from Academy of Scientific and Innovative Research, CSIR, CSIO campus, Chandigarh, India. He completed his postdoctoral research from University at Buffalo, Sunny, New York. He is currently working with CSIR CSIO Chandigarh as a senior scientist. His research interests include optimal state estimation, image processing, computer vision, and machine learning. Welcome, sir. Welcome to you, and over to you, sir.
Thank you so much, Kirti. So I guess I can upload my
So
presentation right.
sorry to interrupt you. There is
Please,
a
please go ahead.
tradition that our HOD sir also welcomes our guests. So I will request HOD sir to please enlighten with your kind words and please welcome our guest.
Thank you, ma'am. Thank you very much. Good morning to everyone. Respected guest of the day, Dr. Shashi Poddarji, all participants, HODs, faculty members, and staff. Once again, good morning to everyone. This department, this is fourth day FDP we have reached. It was planned for 5 days. And all great visionaries and academicians, scientists, they were all present in this FDP. And now Dr. Shashi Poddar is another scientist available. Sir, we welcome you at this juncture on behalf of management, GL Bajaj, EC department, and GL Bajaj Institute with staffs. Thanking you a lot to sparing some valuable time and giving us some enriched value of information on sensor technology. Sir, the word sensor, when it is just spoken by someone, means it intimates us that in this world, nothing is possible without sensor. So naturally, sir, we are very much eager to listen your speech, your technology, so that we can do something in our future. Once again, I am thanking you, sir, welcoming to this platform. You have spared some time for us, and thank you very much, sir. You can take the screen, sir. Thank you very much.
Thank you so much for your awesome, I would say, a very good welcome and good morning to one and all. So I'll first try to upload my presentation and please let me know when my presentation is up.
Yes,
On,
sir,
sir.
screen is
Okay.
visible.
Okay. Okay. So now I'll be giving a brief outline of what I have worked in the past in the area of sensor fusion and its application for autonomous vehicle navigation.
Can you go for full screen presentation, sir?
Sure.
F5.
Yeah. Is it visible now? Is it visible now?
It is visible, but we are not getting full screen. That is F5. आप देखिए सर करके थोड़ा सा.
Sir, right now we are only witnessing, means we are seeing other slides also. It's not full screen mode.
Okay. Now, is it visible clearly?
No, sir. Might be you can stop sharing your screen and again try.
Just
Please put in the full screen mode, sir.
yeah, it's currently in full screen mode. I don't know.
No problem, sir. Go
Okay,
ahead,
sir.
sir.
Yes.
Go ahead.
Then please continue, sir. No problem.
Okay. So now, I hope it gets sorted out, or else I'll just my information will still be visible. So I hope
Yes,
it's
sir.
not an issue. So
You can sir
I was
zoom more. You can increase the zoom. Means it's 84%. You can zoom it out. Might be little bit. 100%. Yes.
so yeah. So I was discussing about the sensor fusion and its application for autonomous vehicle navigation. So when we say autonomous vehicles, there are a lot of things that come in autonomous vehicle. The two main aspects or the motivation behind working it was like one is the Mars rover, the other one is humanoid robots. So in humanoid robots, if you want a vehicle or if you want a robot to move from one place to the other, it should autonomously be able to move from one point to the other if it is A and B. So if you would be knowing, GPS signals are generally not available inside a building. Our mobile signals are available, but GPS signals are not. Similarly, if a vehicle goes on a Mars or any other planet, or if it goes underwater, or if it goes under mines, in those cases, the cameras, the GPS signals are again not available. So how will a vehicle navigate from one place to the other, or how will we come to know how much a vehicle has moved? So people came up with the concept of vision-based navigation and inertial navigation, and further a fusion of both of them. So I started my research with inertial navigation. In inertial navigation, we have three kinds of sensors which are used for navigation. One is accelerometer, other is gyroscope, and third is magnetometer. And if the output from all these three sensors are combined together with GPS, we say GPS aided inertial navigation. And the output of it can be the three-axis information in orientation and the three-axis information in terms of translation. So initially, the work that I started was estimation of orientation, angle, or attitude in all the three axes. So now, let's first see what is gyroscope. So a gyroscope basically measures the angular rotation of the gyro along its own axis with respect to an inertial frame. What it means is that it will keep measuring the three angles in all the three axes if we have some sensors applied over it. So earlier there used to be mechanical gyros, then MEMS gyros came into picture, and then also optical gyros. However, optical gyros, that is fiber optic or ring laser gyros, are very costly, and that's why MEMS gyros are very much preferred in different kinds of application. One example how these gyros are performing or working is like if you have a light source on the left side, and and if the signals are sent in anti-clockwise and clockwise direction, then the detector on the right on the bottom side will detect the phase difference, and this phase difference will be basically be equivalent to the speed at which this whole light or whole system is rotating. So the output from this gyroscope can be directly integrated to give us the orientations, that is roll, pitch, yaw in x, y, and z axis. However, this gyroscope has a very good frequency response in a high frequency, and a low frequency response or a dynamic response or a changing response in the low frequency. So it does perform good when we have high angular motion. So the output from the gyroscope can be converted, or if PQR are the measurements from gyroscope, it can be converted into phi dot, theta dot, and psi dot in these terms. Now, But can we really use gyros directly? The answer is no. For reason being that gyros have varying bias. These varying bias have basically lead to increased error over time. So we need some extra sensors in order to compensate the effect of errors from the gyrocells. So we have something called as accelerometer. How accelerometer works is accelerometer tries to measure the acceleration that and at a specific axis. So if suppose we have a displacement of a particular mass, it can be represented with the help of spring constant of the normal physics. And this is kind of a setup in which a space accelerometer works. The attitude estimation from accelerometer. Now, we know that the accelerometer can give us acceleration, but the output from accelerometer can also be converted into the roll and pitch or the phi and theta angles by applying some trigonometric functions. Now, the output of or the dynamic response of accelerometer is such that it has a very good frequency response in the low frequency and a dynamic response or a changing response in high frequency. And the same goes with the magnetometer. But a magnetometer can be used for estimating the yaw angle, which has a very good response in the low frequency, but a dynamic response or a changing frequency response in the high frequency. So you can see that we have accelerometer, we have gyros, and we have magnetometer. So gyroscopes, which are performing very good at high frequency, whereas accelerometer and magnetometer, which is performing bad in the low frequency, like performing bad in high frequency, can be combined together to yield a good information. Now, but before fusing the output from different sensors, let's see how a sensor data can be used. So basically, we have the initial information that comes, or raw information that comes from sensor is uncalibrated data. Here, if you see, when we do not have any motion or any information, like on the gyros or on the accelerometer, we see this basically a very noisy data. Similarly, the blue point here, this is basically corresponding to 9.8 meter per second square. That is the G value, and the green and the red portion here, which is shown just in the down portion, is basically corresponding to acceleration in x and y axis. So how do we remove this? So there are two kinds of modeling. One is deterministic modeling or deterministic error modeling, and other is the non-deterministic. In the deterministic part, we try to estimate the deterministic or systematic errors like bias, scale factor, non-orthogonality, thermal in-run stability, and repeatability using standard calibration procedure. Whereas the stochastic processes are estimated using modeling techniques. I'll just give a brief of how this modeling and this deterministic processes or calibration process works for an inertial sensor. So now, for deterministic errors, these are the 4 different kinds of errors for which I have worked. So in this, what happens? Bias is any particular output, so for example, if you have a sensor and if you are not feeding any input to it, but if it still gives some output, then that is actually called as bias. Similarly, the scale factor is something like if you give an input of 1, if the output is shown as 1.1 or 1.2, that scale factor error is basically 1.2 or 1.8. And non-orthogonality error is basically that if suppose you have in this figure XP, YP, and ZP as the perfect orthogonal pair, and XA, YA, ZA to be the misaligned pair. In that case, we can have different angles: alpha XY, alpha XZ, alpha ZY, and alpha ZX, and similarly alpha YX and YZ as the non-orthogonality error in all the 3 axes. Misalignment error are similar to non-orthogonality. It is just that misalignment error is compared with respect to a platform, whereas non-orthogonality is compared with respect to system's own axis. Now, how do we estimate the the error of accelerometer? So, what we can do is we can the output that is coming from accelerometer can be said that it is y up is equal to b plus 1 plus s times of k. That is the sensor measurement when the sensor is kept in upward direction. Similarly, y down as the sensor measurement when it is in the downward direction. Now, if we add both of them, y up plus y down, and divided by 2, we can get the value of B. Similarly, the value of S, that is the scale factor, can be obtained using this adjustment of Y up and Y down with the K factor. K factor here is the gravity constant for accelerometer. For magnetometer, it would be basically the Earth's rotation, magnitude of Earth rotation rate for, it would be the magnetic field at a particular axis. And this was basically the part of calibration, and this is a part of stochastic estimation or stochastic error modeling. In this, we try to obtain the Allen variance and the output of basically the frequency response of the sensor noise with respect to time, or the quantity, the amplitude is plotted, or it always gives us this kind of graph. So depending on the kind of slope, we can actually obtain the different kinds of noise, that is angular random walk, bias instability, rate random walk, and rate ramp. And with the help of this, we can estimate different types of noise in a sensor. Now, once we obtain the error parameters, we can actually calibrate and compensate the noise. And the output, which was earlier shown very, very hazy, or you can say very much changing, now is very perfect and is shown here. That is output of inertial sensors after calibration. Now, once we have the output which is calibrated and compensated, we can send that to a Kalman filter. A Kalman filter is one of the techniques which is very popular for sensor fusion. So I'll spend some time on Kalman filter and then go about discussing about different adaptations of Kalman filter on which we have worked here in the research lab. So now, a Kalman filter is basically a system which is represented as XK.
Sir, sorry to interrupt you. I think your slides are not moving.
Okay, which slide as of now
yes,
are you?
Now just it's showing Kalman filter.
Okay.
And the previous 2 slides were not visible. It was stuck on the gyroscope slide.
Oh, is it? Okay. Now is it visible?
Yes, sir.
Okay. Actually, I don't know. There is some issue with the presentation mode. If I'm putting up the presentation
I think
mode,
so, sir. You need to share the complete entire screen. Then might be or the screen will be in full mode. We will be able to witness.
Okay. Let me do that.
Yes, sir. Now it's now in full mode.
Okay, good that you told me in the very important phase of the presentation.
Yes.
Now we are
and sir, you can press on hide button below it so that anyone cannot be missed. Okay.
Yeah. So now now we are currently into the section of Kalman filter. So what happens in Kalman filter? The very important part is representation of system mathematically. Okay. So if we have a system state represented as x and the state vector at kth time instant, so xk can be represented as a times of xk minus 1 plus b times of uk minus 1 plus wk minus 1. Now let's see what are all this. A is basically the transition matrix. Then B is your input matrix, where U is a control input, and W is the noise part. Similarly, the first equation is basically the process model. The next equation is the measurement model, where we say Zk is equal to H times Xk plus Vk. H is here the measurement matrix. I have a small example. We will see that, so that will help us understand how everything here works. So now, let me explain the algorithm first. So, if suppose the error in any time instant can be represented as xk minus xk cap, then the error covariance of it can be represented as pk, which is equal to estimation of xk minus xk cap into xk minus xk cap transpose, and which is propagated in time to provide us xk cap is equal to xk cap minus plus kk times zk minus hkxk. Gk minus hkxk is basically called as the innovation part, or the error between the measurement, where Gk is the measurement, minus the h times of xk cap minus. So this is the propagated part, this is the measurement part. Once we take an error of both of them, we actually keep adding errors at each time. The whole Kalman filter equations, or the like, it can be explained in 4 steps. That is, the first step is project ahead, in which we are trying to estimate the next time instant. Then we try to compute Kalman gain. Then we do an update on the measurement, and then compute the error covariance at each time instant. So this keeps on running at each and every time instant, and we keep getting a better estimate of any state given this principle. Now, before going to this is basically the estimation framework of UAV or any particular vehicle attitude parameter via Euler angles. But before going ahead with this, I'll just introduce a small example how Kalman filter work for a position estimation system. So for that, I'll take the example, or like this is basically a tutorial slide or tutorial presentation by Dr. Dan Simon. So Dan Simon has written a very good book on Kalman filters. So what he does is he also represents the system using this state equation and the output equation. In this, if suppose we are considering that the velocity of any object can be represented as Vk plus 1 is equal to Vk plus t times of uk. Here uk is basically the acceleration and t is basically the time. So delta time, what you say. So acceleration into del t is basically the velocity, and Vk delta is noise. Similarly, we can say, so once we have, and we can also represent Pk, that position and k plus 1 is equal to Pk plus delta t times of Vk, where Vk is the velocity, and plus half. So this is basically the general physics equation of position and velocity. And let us consider Pk and Vk are the system states, that is position and velocity. It can be represented as xk plus 1 is equal to this particular matrix, where xk plus 1 is equal to xk plus p times of pk. So we can represent it like this. So now you can say here, this 1t01 is A matrix. T square by 2 into t, and t is basically the B matrix. Yk is equal to y10 xk. This is basically h into xk and zk. Now here what happens is, if suppose we can, if we estimate this, if we apply the Kalman filter on this equation, that is kk, the xk plus and pk plus 1 equations, where here, so what we can estimate, we can keep estimating the position at every time instant. So the whole, this particular presentation or this tutorial is available even on the website. And over here, if suppose we are feeding the exact data, that is the 10 acceleration as 1 foot per second square, acceleration noise is 0.2, and the position. So if we apply all these things, we can actually get a real equation. And if we actually try to simulate something, we can do that. So Professor Dan Simon has also provided the whole MATLAB equations for simulating this kind of systems, and also the error if we keep changing the acceleration noise or keep changing the measurement noise, measurement parameters, and we can see how a Kalman filter works. Currently, this system has been defined for a linear system. If we have a nonlinear system, we have systems called as nonlinear Kalman filter or uncentered Kalman filter. However, we'll not go much detail into that. Now let's come back to the state estimation of a UAV or any unmanned vehicle. In this case, basically phi dot, theta dot, and psi dot are the orientation angles, the derivative of them, and this biases in all three of them are represented as BP, BQ, and BR. The derivative of the biases is basically represented as noise in this, and these equations are basically taken from the dynamics of flight stability and control by Atkins and Reid. Similarly, a measurement model is defined in this way, where we have the output from accelerometer, output from in all three axes, which can be represented like here. So once we use the equations for the process model and measurement model for a simple position estimation system. So now what will happen if suppose we estimate an attitude using process model alone. So you can see that the reference here shown in green and the estimated here shown here in blue are a little bit off, as in like they're not completely following each other for roll, pitch, and yaw. Similarly, if you see using measurement or model alone, you'll see that the estimated and reference has a lot of basically noise here. Now, if we combine both of them using an extended Kalman filter, the output is much better actually than both of them. So this is just a small example how a EKF or a Kalman filter helps us. So, but now let's see about the equations of Kalman filter. It had basically xk plus xkk, Kalman gain kk, and error covariance. In all these three equations, there were two parameters, that is qk and rk, which had to be fed manually. So there were some researchers who did some work on tuning them Q and RK automatically. Some people have used particle time optimization and other optimization technique. So one of my initial research works, there was a new research, optimization technique called as human dynamic opinion dynamics, or also called as HOD technique. In this, basically, it works on the concept of opinions. So, if suppose there are 100 individuals in a room, and everybody has an opinion about something. So, slowly, if they keep interacting with each other, slowly their opinion will all converge to one opinion. And this was the concept of human opinion dynamics. And I'll not go into the mathematics of how human opinion dynamic works, but this technique was applied in such a way to obtain the Q and R automatically once a estimation error threshold, estimation error reaches below a particular threshold. And if suppose you see this case of when we have a non-optimal noise, that a non-optimal Q and non-optimal R. So this is the case when we have small process and large measurement noise, that is small Q and large R. So this is the kind of estimation result. When we have a large process and small measurement noise, we have this kind of estimation result. But when we tune it using HOD or human opinion dynamic technique, we have a very good results, which is matching to the reference. Now, before going to the next slide, if suppose somebody has any question, we can take some questions on the tuning and anything on Kalman filters.
Actually, there is a request in the chat box that could you please deliver slowly, sir? I can't even follow the slides, so might be the slides.
Okay, yeah, okay, okay, that is fine. I will slow down. Anything else? If anybody has any query,
participants, if you want to interact, you can unmute yourself and you can directly interact with the speaker if you have any query or want to understand some concept which you missed. So we are curious that after gyroscope, what the two slides which we missed?
Okay. After gyroscope, basically I did introduce the accelerometer and magnetometer. So basically, this is the attitude estimation using gyroscope. Then we have the attitude estimation using accelerometer. That is, from accelerometer also we can estimate the phi angle and the theta angle. And using magnetometer, we can estimate psi. So basically, there are three angles: phi, theta, and psi. Phi and theta can be estimated using accelerometer. Psi can be estimated using magnetometer. And phi dot, theta dot, and psi dot can be estimated using gyroscope. So if we take an integration of all three angles, and we can then fuse them together with the output from accelerometer and magnetometer in a Kalman filter setup. Is that fine?
Yes, sir. Definitely.
Okay.
Please continue.
Fine. Okay. So now let me now switch to the next part of my presentation, that is sliding Kalman filter. So until now we saw how a extended Kalman filter works. That is, it takes the input xk cap, multiplies to hk, takes a measurement here, and we have Kalman gain kk to yield us xk plus. Xk plus is basically the post next state estimate. Now, this is the part of simple Kalman filter. When we have a sliding Kalman filter, we have xk cap, we have xk cap minus 1, x cap k minus n. That is a window of past n states which are combined together to yield us a better state. This is a part of sliding Kalman filter. So now, what is the advantage of sliding Kalman filter? So it is something like, if you are having an information about something from just a previous state estimate, then it is good. But if you also have some idea about what happened even earlier, then you can use all of those information together to give us a better estimate, even better estimate. But now there was a question, a question aptitude, or a question that I myself framed or hypothesized. That is, how much previous should we go? Like, is there a rationale that how much should be the size of this n? So this is a mathematical equation how a sliding Kalman filter works. I'm not going to each and every step of it. So, but we can only see the research aptitude question here, that how will you select the length of n here. So now, um, uh, after doing some simulation for sliding Kalman filter with different window sizes, it was found that different window sizes, if you're selecting different window sizes, we are having different MSE values. MSE here is mean square error. If we take for all three angles, and we found that a window size of 40 was giving us a good result. But how will a system understand whether it is good, whether 40 is good or 25 is good? Because this keeps changing on the data set. So now, this was the simulation results when we see that of a extended Kalman filter and a sliding Kalman filter with a window size of 30. Now, there was also a concept of innovative adaptive estimation or adaptive Kalman filter. In adaptive Kalman filter, we obtain the Q and R value automatically. Over here also, we try to have a theoretical covariance which is CVK and practical covariance C cap VK. Over here also there is a practical covariance is also computed like we are taking a window of past error that has been computed. So the concept was again same, or the question was again the same. Can we actually change the size of this window? So we did some simulation of adaptive Kalman filter with different window sizes. For a small window sizes, the mean square error was very high. For a window size of 80 and others, the 80 seemed to be much better. And this was the result of adaptive Kalman filter, or IAE, with a sliding window size of 80. So now, how about having an adaptive plus sliding Kalman filter, SKF plus AKF? SKF plus AKF yielded good accuracies, and again it had a basically window size limitation, that we had to select window size on our own. So then we came up with the concept of change point detection. Change point detection is something like, if suppose you have a data stream coming, and if we can automatically detect that when has the change occurred in the data, so that point we can send to the algorithm that whenever a change is occurring in the data, we will send it to the algorithm, and accordingly the n will get flipped over there. So I used we researched on different kinds of change point detection, and came up with used this particular technique, that is HDCPM, change point monitoring, which proposed by Hawkins and Deng. He had this kind of framework in which he ran man-Whitney test and reinitialized data. When we applied HDCPM, still the algorithm was not working fine. So what we did, we had to apply some pre-whitening in the data. Pre-whitening because the data was auto-correlated among itself. So in order to remove the auto-correlation between the data, we did a pre-whitening, and then the concept of ASKF was evolved, and it yielded very, very good information or accuracy in terms of the output. So it yielded better information than even normal SKF or SKF, adaptive Kalman filter, and a combination of SKF plus AKF. So the output of ASKF is also shown here. You can see visually also it is much better than either of the adaptive Kalman filter, sliding Kalman filter, or normal AKF. So now from here onwards, working on another concept, that is the complementary filter. Complementary filter is comparatively no inverse comparison. You just directly have to pass the output of accelerometer to a low pass filter, the output of gyroscope to a high pass filter, and combine them together. But so this is the concept of a simple Kalman or a linear Kalman filter. Mahoney, Madvick, and several other researchers came up with the idea of nonlinear Kalman filter. Nonlinear Kalman filter had two parameters as Kp and Ki. This Kp and Ki were again fed manually. So since I was already working on adaptation of different Kalman filters, we thought, how about adapting these parameters of complementary filter? And then we applied particle swarm optimization to adapt the Kp and Ki. Some of the researchers had already worked on application of fuzzy logics in order to adapt this Kp and Ki. The application of evolutionary optimization technique was very new in this area, and it yielded good results. And this is the kind of algorithm structure that we followed. That is, we waited until 30 readings, applied PSO on average of last 30 errors, and basically populated the whole framework using different Kp and Ki possible parameter values. And once the error value reached a particular threshold, we used to stop the algorithm, saying that yes, the PSO has now found out the suitable Kp and Ki parameters. The results related to this were like, if suppose we have different Kp, Ki values, we had different average RSMS values. But if suppose we apply PNCF or like PSO added nonlinear complementary filter, the output was even better. That is 0.07 here, 0.04 here. It is much better than either of any combination of Kp and Ki. These results we compared with different other algorithms, that is Mahoney, Madvick, and Hong. Hong was a paper which applied fuzzy logics. And this was also compared on two different kinds of data set, that is XSense and Ardocopter data set. XSense is a very good sensor suite provided by XSense company, and Ardocopter is again another sensor suite which is accelerometer, gyros, and magnetometer on one unit. So we had these two data sets generated in our lab, and accordingly we were able to achieve good results in this case. This is the kind of results for all four. You can see that all of them seem similar. It is just that you can say when we see the error part, we can actually realize how much is the difference between all of them. So this was published in Intelligent Robotics and Systems. Then we also came up with the concept of multiple model adaptive complementary filter, in which we had stacks of complementary filter with different kinds of window size, you can say, or different parameters in each of them. So once we had different parameters coming with different Kp, Kis, we combined them together probabilistic in an MMACF or MMAE framework and yielded an output, which was again published. And the output is again visually, you can say, is much better than the other, which is without any adaptation. This is the work which has been published just 2 months back, which is like cascaded complementary filter architecture. In this, one of my students, like Parag, he's currently working with Symbiosis. So we work together on basically combination of a linear complementary filter along with a nonlinear complementary filter. And this has yielded very, very good performance, as in it does not require any adaptation, and has been published with MDPI census. Now, I'll give a brief of my small work that I did during my postdoc research. But before going to that, if anybody has any questions until now, may please tell me. We can take up those questions before going to the next part of the presentation.
Participants, if you would like to have interaction with the speaker, you can unmute yourself and ask any concept which you missed, or you want to have a small explanation. You can ask the speaker. Or you can write your query in the chat box. I will bring it up to the speaker. Okay, sir. I have a query. Means you are showing your innovative algorithm where you are instead of that theoretical covariance, you are setting up practical covariance set, right?
Yeah.
So how you are deciding the threshold for your algorithm?
The threshold basically we are deciding depending on the empirical results that we are wanting to achieve. If you know that our system has a actually all the algorithms has a set threshold limit beyond which even if you keep iterating, the systems will not perform better. So we basically keep experimenting, and on the basis of that, we yield those threshold values.
Okay. Because you can also throw some light if some participants, if they would like to work on this topic and they want to deliver, means they want to have their own experiment set up on sensors and they want to apply this algorithm, then what you will advise them means. Just
See, the students or like anybody who wants to work on inertial sensors on something, nowadays I guess MATLAB also has some data generation setup. So, and some algorithms are already available online. So directly one can start from there, implement like already existing algorithm, and then from there onwards start reading some literature. And if any help is needed on any particular algorithm implementation, I can help them out with any information needed. If somebody wants to work specifically on an algorithm which we have already worked, we can share some more information on that.
Okay. Because I had also worked on a little bit similar aspects. I will be reaching out to you.
Sure. Most welcome.
Okay. So, sir, please continue. Okay, there is one
Okay.
question which has come from Mr. Ganesh Kagupati. He is asking, are there any works discussing the stability of EKF with unknown inputs?
EKF with unknown input. What is the kind of unknown input? Like each and every time we need the system model to be known. But I'm not able to understand unknown input. Can you please tell me specifically?
So might be is asking in such scenarios where the inputs are like random, they are not known. Because real world environment is something unknown input, things might be like that you want to ask.
For a Kalman filter, actually, specifically, this is one of the disadvantages of Kalman filters, that you need the system to be known. Only if the system model is known to us, we can do a good prediction. In fact, if there is some mistake or some error in the mathematical model of the system, the Kalman filters do not perform good. And this is one of the reasons why we also started working on complementary filters. Okay.
Thank you, sir. Please continue with your session.
Sure. Okay. Now let us go to another concept of fixed smoothness. Fixed smoothness is somewhat little different from the slide confidence. In fixed smoothness, what happens is, if we have past n states, we need to improve the current state only. As in, with the help of information which is available in the past state, we also keep applying the Kalman gain of each and every state to obtain the whole system equations are little different. So what we worked was like that we saw that with different lag lengths, the output of the position estimation technique does not always perform good. That is at this point of instant, you can see that a lag 2 is giving us a like a better estimated like a bad estimation position. Whereas at this point here, if this is the reference, the dashes are the reference, this is performing good here. Similarly, at these points here, a lag of 10 is performing good, whereas a lag of 2 is not performing good. And it keeps basically varying. So the idea was whether we can combine them all together. That is, combining different lagged outputs to yield a good estimation accuracy. So we applied a MMA-based adaptive lag smoother. So, and we obtained the results of MMA with respect to the normal lags. And this was the output with respect to error covariance matrix values. And this result or this particular simulation results are currently under publication, and probably is under review, I would say, and should be out by some time. So now we will switch to the vision-based navigation. So when I told during the initial presentation that for any system to work in an indoor and or an underground or an extraterrestrial kind of setup, in those cases, we do not have GPS signals, but we have cameras. So cameras can be used for estimation of navigation parameters. This is a basic pinhole model of a camera. I'll not go into the basics of the vision-based navigation. So if you have a world point here and an image point here, you can actually represent the image point using a projection matrix P and a 3D point, and a 3D point X can be basically mapped to a 2D point. So now, let's consider we have two images over here on the top, here on the bottom. So can we do a image stitching, or how would we do an image stitching in both of them? So first we will detect the images or feature points in both the images and find corresponding pairs in it. These are the feature points that have been detected. And then we do a feature matching. Once the feature matches are done, then we can find that to what angle it has to be rotated and translated so that they both can be stitched together or combined together to yield a bigger image of the same of a similar area. And you can see that how they are aligned together to give us a much bigger picture of the like fragmented images. So now there are different kinds of these feature detectors. Few are some of them are single scale detectors, which was proposed initially in 90s. Basically single scale detectors like Moravec, then Harris corner detector, and several other corner detectors. But these detectors were not able to work on different scales. That is, if suppose a car is bigger in one image and if the same car gets smaller in the few more images, then that same car will not be detected by the single scale detector. So we needed a multi-scale detectors. So there came a concept of SIFT. SIFT was proposed in 2004 by Loic, and since then several other feature descriptors and detectors have come into market, like SURF. Then we have Brace, ORB, and several other detectors and descriptors. So what happens here is we have different scales of images which are combined together to yield a histogram of versions. I'll not go into the detail of how a feature descriptor is made. And yes, you can for the purpose of representation, I can say that yes, it will give us an output of a particular point in terms of a vector, which is unique to that particular point. So there are also different kinds of feature matching techniques. There are exhaustive search, there are hashing techniques, there are nearest neighbor techniques. I'll not go into this. Now, once we have the images captured from suppose let us you can like this some images. Yeah, so we have some images here, left, right, over here. So how do you estimate approach or the parameters of navigation? That is, suppose the vehicle has started from here and has reached here. How can we calculate that? So I'll not discuss that, how does it happen. So the whole pipeline can be described in this way, that we have images coming up, feature detection, feature matching, landscape-based 3D motion estimation, post-concatenation. Let's see how each of them perform. So now let us consider we have two images, left and right, at the initial time instant. At few next time instants, we again keep getting images. Now what do we do next? We try to detect features in the images here. So let's see on only the first two images here, that is TK and TK plus 1. So we have these feature points here. Once the feature points are detected, these are basically matched. So first we do intra-frame matching, that is left and right. So this point here is matched to this point, which is an outlier. This point green is matched to the point here. This electric pole is basically matched to the electric pole. The car is matched. The car headlight is matched to the car headlight, and so on. Now, there are several techniques to remove outlier. One of them is epipolar constraint. So once we do intra-frame matching, we do an interframe matching. You can see here that this portion of the tree is matched to the shadow of the another tree. So this is again an outlier. This again has to be removed. Once these outliers are removed, we get perfect matches. Perfect points which are there in all the four images, left, right, and up and down. Once we have all these four images, we basically what we do is we can say this as U-shape matching. Once we have these feature points, we basically try to triangulate them. Triangulation is a technique by which we can actually obtain the 3D point corresponding to the 2D image points. Once strangulated 3D points are obtained, we send them to Ransackbet's 3D motion estimation. So it works like this: that if you have a 3D point cloud on the tk minus at tk minus 1 time x time,
I think the speaker lost connection.
Sorry for the inconvenience. Let me call to the speaker first.
Okay.
Sorry for the inconvenience for all the participants. Actually, the keynote speaker facing some issues regarding his internet. So he will be here in 2 to 3 minutes.
Okay, ma'am.
Hello.
Yes, sir.
Hello.
Yes,
I
sir.
guess I got disconnected.
Yes, sir.
Uh,
No worries, sir.
at what slide did it got disconnected? By any chance, can you let me
Uh, participants, Kirti ma'am?
Sir?
know? What was I discussing when it got disconnected?
I think so.
Okay,
It was
okay.
I.
So you are
I
discussing
case.
about the sensors, the non-linear errors which you are discussing
Okay, had I discussed
from
the complementary filter? Okay, I
audiometry,
guess.
audiometry. You are
Okay,
discussing about audiometry.
okay. I'll resume from the odometry part in that case.
Yes, yes, sir.
Okay, okay. I had this slide been presented.
So your screen is not visible.
Okay, no, just a second. I have to present again.
Also, some of our participants are saying means like background noise about which is coming at your end. Can you request that slightly
Okay,
up?
let me try that.
Okay.
Yeah, I hope it should be better now.
Yes, yes, the same slide. Yes, yes, yes.
Okay.
Vision means
Okay.
navigation.
Okay, so fine. What I was telling that with the help of images, we can actually estimate the pose information, that is the rotation and translation of the car or any vehicle which is moving. Now, how do we do that is we can actually, this is a big pipeline, that is we take the images, detect the features, do some feature matching, apply ransack-based 3D motion estimation, and post concatenation. So let's discuss how do we do that. So once we have the output from the images, that is left and right images at different time instant, then what we do is we can actually detect the features first. Once the features are detected, you can see the features are detected at the corner of the car, on the back side of the car, on the trees and the poles, and on this car. Now, the same features are also detected on this particular image. Now, how do we do a matching? There are different techniques of doing feature matching, but you can see that there are at times outliers or mismatches. So this point of the tree is matched to the top of the car. This point in the electric pole is matched to the electric pole. So how to remove outliers? One of the technique to remove outlier is basically epipolar constraint. I'm not going into detail of how the constraints work. So now once intra-frame matching is done, then we also do inter-frame matching. But you can see our outlier again. A portion of the tree is matched to the shade of the same tree. So we also need to remove these outliers. There are different techniques of removing these outliers again. Once these outliers are removed, we have perfect matching in all the four images. These matches are then basically triangulated. That is the image points in the left and right are triangulated for the first frame and same for the second frame. Now you see we have 3D point clouds of the previous time instant and the current time instant. These 3D point clouds are basically sent. There are different techniques of estimating motion out of them. One of them is ransack-based 3D motion estimation. Now, ransack-based 3D motion estimation works. Let me explain you that in a few steps. Now, if suppose you have 2 points here, the target here is to obtain the best line that matches the two lines, that matches the 2 points here. So we can randomly select 2 points and draw a line out of this. and we see how many points are basically falling near to it, and we calculate distance. The same thing we'll do with two other random points and two other random points. And one time will come that we'll select the two like points which are falling to the maximum number of points. This is the perfect line for this particular points, or the most like you can say suitable line. So this kind of algorithm, this is currently for 2 points, whereas for rotation and translation, we have 6 parameters, 3 for rotation and 3 for translation. And we do this with the help of algorithm to estimate the best fit using several iterations of answer. So once you obtain this rotation and translation, that is transformation parameter, we then concatenate these poses together. Once the pose concatenation is done, there are several algorithms by which we do pose refinement also, and we obtain an output of this kind. This is the output of basically a Kitty data set, or like self-driving car. So in this case, camera is mounted over the car, and as we keep moving, our basically you can see the pose graph here, or a path taken by the vehicle. It keeps changing. This is currently in 2D framework, but it can also be represented in 3D. So once we did several works related to improvement in VO pipeline. One of them was like reducing the feature length. Some of them involved uses of inertia. The recent work that we did was uses of mutual information to reduce the number of features that are sent to the whole pipeline of VO. So what happens is, if suppose you have 100 features, if you have 100 features and if it is sent to a pipeline, if it is, suppose let us take that it takes 10 seconds. So the hypothesis here was that can we reduce the number of features and still achieve the same accuracy? So we applied mutual information or computed mutual information different features. Once the mutual information was computed, we realized that yes, there were several features which are belonging to the same headlight area, several features which are belonging to the same area of the image. So why to keep them over there if it is yielding same information? So by reducing the number of features, accuracy achieved was similar, and whereas the time taken reduced. This is the kind of like performance that we achieved here. And Evo 64 is the feature with the feature length of 64. With 32 is basically the feature length, and 16 again is the feature length here. This is the output of Kitty dataset, and this is the output of the Europe MAB dataset. So this particular dataset basically flies the MAB inside a building, and ground truth here is presented in DAS, and green here is the standard MIVO, and the standard VO pipeline, and MIVO is basically the proposed framework. And you can see here that the output closely follows the green path here. And so we were very convinced that yes, this performance algorithm works fine. And it was also published with the Journal of Intelligent Robotics and Systems, Springer, recently. This work was done in 2020, I guess. And now currently what we are working is a vision plus inertial navigation system, the combination of both of them. So in this case, our Kalman filter will basically have camera states and also the inertial sensors, or the pose like the states from the inertial sensors. So we are combining them together to estimate or yield better pose estimates. So this is also the base framework for SLAM kind of system, simultaneous localization and mapping. And this has this kind of systems have applications in unmanned vehicle navigation, robotic surgery, augmented reality, satellite to satellite docking, and GPS denied environment navigation. So with this, I come to the theoretical end of my presentation. But yeah, if you have some queries, we can discuss that.
We have a question, sir, in the chat box
Okay.
by Dr.
I should
Kirti
switch
ma'am.
here.
What type of MEMS-based sensor you are using for feature detection?
Okay, for feature detection, so when we discuss about feature detection, that is basically the MEMS, that is basically the camera that I am talking about. So in camera, we are not using anything related to MEMS sensor, but we are basically using the feature detection, that is SURF, is that which we are using currently in our algorithm pipeline.
Okay, so thank you for answering. Please continue with the session, sir.
Yeah, so my theoretical portion is now completed, but now I would expect that if you have some specific queries, I can answer those, or else we can like take up, like I can explain something related to the image part.
Participants, if you have any queries, our speaker is available to interact with you and take your queries.
Dr. Shashi sir, एक problem. I have one
Yes.
question.
Yes, sir, please go
If
ahead.
we are studying for gyroscope sensors, normally gyroscope I have studied. Normally it is used in all aircrafts and all, which gives turn and slip indicator. Aircraft is turning or rolling, so that technology it
Yes.
is used. That was a mechanical technology. So if that sensor, gyroscope sensor, if it is used in the vehicle, so can we have a display in front seat that we are turning by this much degree or this much degree, or sharp turn you are taking, or a 90-degree turn you are taking? So is there possibility of such sensor that it should give information in vehicle?
Yes, very much. In fact, all our mobile phones now currently have this accelerometer and gyroscopes. So now if suppose you would see that some of the mobile phones have that application that if you turn the mobile on one direction, it will basically do something, like it will switch on a particular application. Similarly, some mobile also has, so all the, in fact, current devices which are used even for our navigation in the mobile uses those accelerometer and gyroscopes. So you're right, we can
Right.
use those to represent the information of orientation and the vehicle navigation.
Okay. Thank you, sir. Thank you.
Yeah. Welcome.
Participants, we will request you, the speaker is available. Please feel free to interact.
Yeah, I
The
feel
topic
if
is
you,
being
yeah, yeah, I feel if everyone interacts, it is more a kind of a learning experience for both of us, because lecture is one-sided delivery. I believe more in interaction with everyone. So, because that is how we will learn more. If you have some specific queries or something which is related to your ongoing problem, we can discuss if it is related to this topic also. If there is any specific
are
portion of the
waiting.
presentation that is basically missed out, I can repeat that portion as well.
The topic, if you feel that in any slide which you have not been able to understand, you can also write the topic. The speaker can make you understand that particular topic as well. Okay, so might be it was a very good session and everyone have understood. We are assuming because it's being new, so sometimes the when you are means
Right. This was
exploring.
really latest technology,
Yes,
and people they have to be very aware of what knowledge you have given. That is, we have to study in depth. And really, I'm very much interested to learn what you have said in this technology. And this automation, particularly suppose some company like we should share this knowledge to our students, because same company sometimes it is coming boss which is going for automation. All vehicle automation is carried by boss. So if this technology can be shared to our student, it will be very beneficial in placement. So
And
whatever I
in
have
fact,
learned, naturally I will share this. I will ask my student what is automation, what sensors we are using. So I'm
in
really
fact,
thankful to you, sir.
currently all the car manufacturers are actually working towards autonomous navigation. In fact, not like you cannot miss one. In fact, everyone is working. So, and this is basically the base of all of them. Most of our
Correct,
students who
correct.
passed from our lab actually, or like who did their thesis, are currently into those kind of companies which are making autonomous vehicles. So
Oh,
yes, it is indeed
yes.
very, very related.
I have seen your technology was very vast and very new to us, and really we should learn, we should study. I'm really very much thankful to you, sir. No doubt,
Thank you so much for the opportunity.
what in limited time you have shared this knowledge. I'm very much thankful to you, sir. And sometimes, and very soon, when everything is open, sir, we will invite you to come to see our college. I will
Sure,
be very
sir.
much thankful to see if you are here on our
Sure, sure,
platform as a physical.
sure,
So
sure,
thank
sir.
you, sir. Thank you very much. Thanks a
Okay,
lot.
okay. Thank you very much, everyone. Okay, thank you so much.
Okay, so we will be concluding with officially with the vote of thanks, and let me just conclude it. So I deem it a great honor to propose vote of thanks to all those who have helped us in making this today's session such a memorable experience. I, Dr. Asta Sharma, on behalf of EC Department, GLBITM, extends a very hearty vote of thanks to our chief guest of the day, Dr. Shashi Poddar, for gracing today's webinar and delivering such an insightful talk. We hope our participants have gained a lot from your session. I would also like to express a profound gratitude to HOD sir, Dr. Satendra Sharma, for his continuous moral support and guidance. Also to our director sir, Dr. Rajiv Agarwal sir, for always encouraging us to offer such kind of programs. I would like to thank all the Department of Electronics and Communication Engineering. Thank you for being such a great team. I would also especially thank Dr. Kirti ma'am for today's speaker, because we know that Dr. Kirti ma'am has known you, sir, and she has recommended your session. So thank you for that. And finally, the wonderful participants for your unwavering attention throughout the session. Thank you so much for your cooperation. Also, we request our participants to be very attentive, and we will be having the afternoon session in which the attendance links will be shared. Please be attentive, be participative, interact with the speakers, because these speakers are specially arranged for you, and we will be happy if you can gain from these sessions. So thank you all. Thank you all. Have a nice day. Thank you, sir.
Thanks a lot. Thanks. Okay.
Thank you
Good
so
day.
much. Yeah, good night.
Okay.